Hi everyone. This video is the small application of matrix products and the row column rule. The application will be to rotation matrices. A rotation matrix, by definition, is a matrix to which that is associated with an angle theta, and the entries of the matrix are trigonometric functions. So fixed in angle theta, the rotation matrix of theta is the matrix cosine theta sine theta minus sine theta cos theta. The reason why this is called a rotation matrix is that it describes a rotation in the plane of angle theta. The way we can convince ourselves of that, so applying this matrix, here's a picture of how the matrix would look like. If I take any vector v in the plane, I can then apply the matrix by multiplying the vector to it, and what I would get is a copy of v rotated by an angle theta. To convince yourselves of that fact, we can try rho theta on the standard vector e1 and e2. If I apply rho theta to e1, I get the following. Let's write it here. We have cos theta sine theta minus sine theta cosine of theta times 1, 0. That's my vector e1. Now, if I apply the row column rule for matrix multiplication, here I get cosine theta times 1 minus sine theta times 0. That's cosine theta. Sine theta times 1 plus cosine theta times 0. That's sine theta. And if I graph the point cosine theta sine theta on the plane, I get a picture like this. A point cos theta sine theta is a point on the unit circle, and it's exactly the point I get by taking the standard vector e1 and rotating it by an angle theta. You can see in this picture that the coordinate of the points are exactly cosine theta for the x-coordinate and sine theta for the y-coordinate. By performing the same multiplication with e2, e2 is a standard vector 0, 1, so it extracts the second column of our theta, minus sine theta, cosine theta. If I were to plot that, I would get exactly what is expected, which means I would get the vector whose x-coordinate is minus sine of theta and whose y-coordinate is cosine of theta. Think about this second picture here as a 90-degree rotation of the first picture we got. When you rotate it by 90 degrees, then your former y-coordinate becomes minus the x-coordinate, and the former x-coordinate becomes your y-coordinate. Now that you believe that rotation matrices act by rotation in the plane, here's a simple fact. If I rotate by an angle alpha, and then I rotate again by another angle beta, that's the same as doing a rotation of the angle alpha plus beta all at one time. So if there's justice in the word, it should be the same that the rotation matrix associated to alpha plus beta is the same as the rotation matrix of rotation by alpha, followed by rotation matrix rotation by beta. Let's try to see what this equality gives us. The left-hand side is the following two matrices. It's rotation by beta, here it is, and rotation by alpha. Let's use the row column rule to multiply, to compute the result here. So the first entry will be first row, first column. It's cosine beta, cosine alpha minus sine beta, sine alpha. The second entry will be first row, second column, minus cosine beta sine alpha minus sine beta cosine alpha. Second row, first column means I have to take the second row of the first matrix and the first column of the second. I get sine beta times cosine alpha plus cosine beta times sine of alpha. And then finally, the last, I take second row and second column minus sine beta sine alpha plus cosine beta cosine alpha. The right-hand side of this equality, I'll just write it here, is the rotation matrix attached to alpha plus beta. So we get cosine of alpha plus beta, sine of alpha plus beta, minus sine of alpha plus beta, cosine of alpha plus beta. Now, if this equality is true, which it is, because it corresponds to the fact of rotating once at once or in two different moments, then the entries of these matrices must match. In particular, for example, this entry over here should match cosine of alpha plus beta, and this second entry over here should match sine of alpha plus beta. That's exactly the upshot of this application. The fact that they do match, you've already seen when you studied trigonometric identities. And in fact, this is an alternative proof using linear algebra of trigonometric identities. The sine of alpha plus beta is equal to sine of alpha times cosine beta. There it is. Plus cosine alpha sine beta. And that's exactly what we showed using these matrices.